Hello everyone, welcome to this video lecture on quantum mechanics. In this lecture, I'll explain the 1D step potential, and this is the plan. We will first describe um, what a one-dimensional potential step is. We will define it graphically and using equations, and then we will consider the two possible cases, case 1 and the second case. For each of the case, we will first write the Schrodinger's equation and obtain its solution, then find the probability of transmission and probability of reflection, which are called as transmission and reflection coefficients, and then we'll see significance of the result for each of the case. In the end, we will consider this negative step potential, and here, instead of solving it completely, I will simply discuss the solutions and the results and discuss what they signify. So let's first begin by defining the one-dimensional potential step. So the potential is like this. We have this as the x-axis and the potential is 0 from minus infinity to x is equal to 0. At x is equal to 0, the potential jumps to a constant value, to a finite value v0, and it stays constant after that for rest of the x-axis. So this is the potential. This is our region 1, which is from minus infinity to 0, where the potential is 0, and this is the second region, region 2, which is after x is equal to 0 to x is equal to infinity. Now you can see that we have a discontinuity in this potential. Remember, this is a simple graph where on the y-axis we have the potential as a, and the x-axis is the x coordinate. So we can see that at x is equal to 0 we have a discontinuity, and therefore while writing the equation we have to write it in two parts, and this can be mathematically written like this: v of x is equal to 0 for x less than or equal to 0, and v of x is equal to v0, a constant value, for x greater than 0. So this is how you can write the potentials, and because of this discontinuity, even when we write the Schrodinger's equation, we have to write it separately for the two parts and then match the two wave functions at the boundary at x is equal to 0. Let's now see that in detail. So let's first write the Schrodinger's equation for this case, for first case where E is less than V0. So this is our first case that we are discussing. This is the potential. X is equal to 0. This height, remember, is V0 even when, if I don't write it, and energy of the particle is now less than V0. So the incident particle, we will for all the, or for both these cases, we will consider that the particle is incident from left and it is traveling towards right, and then it encounters this boundary at x is equal to 0. So the total energy of the particle in region 1 is same as its kinetic energy, because potential energy is 0, and it is now such that E is less than V0 for this case. So particle has kinetic energy less than the height of the height of the step, and therefore classically this region 2 is forbidden. So region 2, let me note it down, region 2 is classically forbidden. Naturally, because the kinetic energy of the particle is not more than the potential, and the particle doesn't have sufficient energy to cross the step, to cross that boundary. And now let's see what we get quantum mechanically. So let's first write the Schrodinger's equation, and since the potential is independent of time, we can simply write the time independent Schrodinger's equation, which is minus h cross square by 2m d2 psi by dx2 plus v into psi of x is equal to E into psi of x. So this is Schrodinger's equation This is the Schrodinger's equation, which is time independent, and V of x is the potential. So let's now first write this equation for region 1, and let's say the solution or the wave function in region 1 is psi 1. Therefore this equation becomes minus h cross square by 2m d2 psi 1 by dx2 plus potential is 0, therefore the second term is equal to 0, and this is equal to E into psi 1x, and the Schrodinger's equation therefore is minus h cross square by 2m, or let me write it like this, let me skip a step and write it like this, d2 psi 1 by dx2 is equal to minus k square psi 1, where k is equal to square root of 2me by h cross square, and note here that k is a positive constant, so k is positive here. Now let's write the Schrodinger's equation in second region, in region 2. Let me do it here itself. So this is region 1. Now I'll write the equation in region 2, and the equation then is minus h cross square by 2m d2 psi 2 now by dx2. I am not writing psi 2 as a function of x explicitly. It is given that psi 2 is function of x, and the second term is now not 0, unlike the equation for the first region. It is now v0 into psi 2 is equal to E into psi 2. So the equation therefore can be written as d2 psi 2 by dx2 is equal to, now this is plus k prime square psi 2, where k prime is this equation 2m v0 minus e by h cross square. Am I right? Yeah, it seems all right, where k prime is again a positive constant. For this case, of course, when e is less than v0, and these are the two equations, or these are the equations, Schrodinger's equation in region 1 and in region 2 for these values of k. Now let's solve these equations. So let me start with region 1. So in region 1, the equation, I'll rewrite the equation. It is d2 psi 1 by dx2 is equal to minus k square psi 1, where k is, let's write it, it's 2me by h cross square, a positive constant. Now here, because of this negative sign, psi 1 turns out to be a complex quantity, and its solution in general is can be written like this. It is a into e to the power I kx plus b into e to the power minus I kx. Now we can see that both these terms that we have in our solution are traveling wave solutions, and therefore they represent a particle which is moving with certain momentum, and this k here represent for any wave in general angular wave number k is equal to 2 pi by lambda, where if we now use if we use de Broglie's equation, where lambda is equal to h by p, then this k is equal to 2 pi by h into p, or it is equal to p by h cross. So if we look at this solution now in region 1, the first term has positive k, and therefore it corresponds to positive value of the momentum, and therefore that term represents a particle which is moving towards positive x-axis, which is moving from negative to positive direction of x, whereas the second term has negative value of the angular wave number, and therefore it corresponds to negative momentum, and therefore it represents a wave, a matter wave which is traveling in negative direction of x. And if we now give a little thought to it, you can think that the first term is basically the incident particle, because that is the particle, we are considering the particle which is traveling from negative to positive direction, and therefore the first term represents the particle which is coming from left to right, the incident particle or the incoming particle, whereas the second term in this region represents a particle which is traveling in negative direction. And when will this happen? It will happen when the particle is reflected from the boundary x is equal to 0. Oh, I'm sorry. So when the particle is reflected from this boundary, we have this second term b into e to the power minus kx. So the first term a into e to the power I kx corresponds to the incident wave, and therefore I can write this, I will write it as psi incident, and the second term it represents the reflected particle, and therefore I can write it as psi reflected, which is b into e to the power minus kx. Remember, k is given here. So this is the solution in the first region. Now let's consider the solution in region 2. Now what do we have in region 2? The equation is d2 psi 2 by dx2 is equal to plus now k prime square psi 2, where k prime is square root of 2m v0 minus e by h cross square. So if we have this as a positive sign in such equations, in the second order differential equations, then the solution is no longer a complex solution. It turns out to be a real solution, and that psi 2 then can be written as, I'll write it with c into e to the power I, no, we don't have the complex solution, it's real now, k into k prime into x plus d into e to the power minus k prime x, where k prime is this constant. Now I want you to give it a little thought. Pause this video here and tell me which of these two terms are not acceptable physically. So please pause the video here and think about it. Okay, so I hope that you have figured out the answer for this question. I'll answer the question on the next slide. So in region 2, psi 2 is c into e to the power k prime x plus d into e to the power minus k prime x. Now we know that as x tends to infinity, psi should go to 0. It is one of the requirement for physically acceptable wave function. Otherwise, it would suggest, if the wave function blows up, if it goes to infinity when x tends to infinity, it would suggest that the probability is tending to infinity, because psi is the probability density, mod psi square gives us the probability, and therefore as x tends to 0, a physically acceptable wave function should tend to, oh sorry, as x tends to infinity, a physically acceptable solution should go to 0, and therefore if we look at this first term, it blows up as x tends to infinity. As x tends to infinity, this first term is going to infinity, it is tending to infinity, and therefore it is not physically acceptable, whereas the second term is fine, because extending to plus infinity, the term um, it is tending to 0. So let me note it down here. Let me use it, let me write it with a different color. So first term is not physically acceptable, and therefore the solution psi 2 is, okay, let's go back to the original color. I guess that will that is more visible on the background. So psi 2 therefore is d into e to the power minus k prime x, where remember k prime is this positive constant 2m v0 minus e by h cross square. Okay, so how do we interpret these solutions now? To interpret these solutions, I want you to recall a concept that we have previously discussed, probability current density. This probability current density we denoted it by J, and for one dimensional case it is I h cross by 2m into psi into d psi star by dx, where psi star is the complex conjugate of psi minus psi star d psi by dx. So this gives the probability current density. It's like uh, how is the probability changing per unit time at a given point. And now we want to consider this probability density for the solutions that we have obtained. So let's first find that for the incident particle J incident. Let's if you go back, J incidence is this one here. So it is okay, A into e to the power I kx, and this is psi incidence, I'm sorry, and psi star, therefore complex conjugate of this wave function is A star, considering that A in general is a complex number, so I have to take complex conjugate of that number to find out the complex conjugate of the wave function, into e to the power minus I kx, because it's a complex conjugate. Now we also need the first derivative of psi incident with respect to x, which is I k a into e to the power I kx, and psi star, oh sorry, d psi star by dx for the incident wave is complex conjugate either of this derivative, or you can separately differentiate this. It will give the same result, which is minus I k a star d, okay, I'm sorry, e to the power minus I kx. So we have d psi star by dx and d psi by dx to calculate the probability current density for the incident particle. So let me write it. J incident, this is equal to I h cross by 2m. Now I'll write psi first, which is I k a into e to the power I kx, and the derivative of the complex conjugate of that is minus I k a star, now e to the power minus I kx. So this is my first term. The second term now has to be written on the next line with a negative sign. Now what I have is a star e to the power minus I kx, and the derivative is I k a e to the power I kx, and therefore J incident, the probability current density for the incoming particle is I h cross by 2m, and you can see that if, oh, this I have written it twice, is it? Oh, this should not be there. This I should not be there. Ah, k should not be there. Already have written it, and I do have a minus sign. Now it seems all right. Okay, so what we have is I k mod a square with a negative sign, and when you multiply these two terms, it will turn out to be e to the power 0, which is equal to 1, minus the second term is also same, it is my I k mod a square. So therefore let me carry this to the on the next slide. So J incident is I h cross by 2m, and if you look at the terms, it will become 2 times each of the term in the square bracket. So it is therefore minus of 2k mod a square, and of course there is one iota I, right? So what we have is minus I square, and remember I is the imaginary number square root of minus 1, therefore I square is equal to minus 1, therefore J incident is, this 2 gets cancelled and I also is not there, so it is h cross k by m into mod a square. So this is the probability current density for the incident particle, for the incoming particle. Similarly, if you calculate J reflection, which is to do with the wave function which is reflected from the boundary of this step, and this psi2 or psi reflection, remember, is p into e to the power minus I kx. Then for this reflected, it will turn out to be equal to, it is same, you can do the calculations and you can convince yourself that this is h cross k by m into mod b square now. So this is the probability current density for the reflected particle. Now let's consider the probability current density for the transmitted particle and see what we get. I'll do it here. Now for the transmitted particle, we have to consider the wave function in region 2. Let's go to that wave function. Wave function that we have here, and it is psi 2 now is, which also happens to be psi transmitted. So let me write it like this: d into e to the power minus k prime x now, and its complex conjugate psi transmitted star is also same, d into e to the power minus k prime x, where this can be in general, this can be a complex number. Let's write it as d star. It's real, we don't have to consider it. The solution is always real because we don't have the imaginary term in the differential equation itself. So basically psi transmitted and its complex conjugate is same, and therefore if you calculate d psi transmitted by dx, which is equal to minus k prime d into e to the power minus k prime x, and d psi star or the transmitted wave function by dx is also same, minus k prime d e to the power minus k prime x. And if we calculate J transmitted now, then is this equation I h cross by 2m, then I have psi transmitted into d psi star by dx, d psi transmitted minus psi transmitted, psi star transmitted, or d psi transmitted by dx. And you can see that uh, since this first term is same as the second term, because now we don't have the imaginary number anywhere which was there in the previous case, and therefore the term when you subtract, in fact didn't cancel but added up to become 2 twice of each of the term. In this case, however, these two terms are same, and therefore J transmitted is equal to 0, which simply means that the particle, the probability current density on in the classically forbidden region is equal to 0 according to quantum mechanics, and it is in agreement with what classical mechanics has to offer, what classical mechanics has to say. And now let's actually find out the the two important quantities, reflection and transmission coefficient, on the next slides. Okay, before we calculate the probability of reflection and transmission, and which are called as um, reflection coefficient and transmission coefficient respectively, let's first we have to uh, uh, complete some mathematical steps to figure that out. We have to do some mathematical jugglery. So for and that what we have to do here is we have to consider the boundary conditions of the wave functions which should be satisfied, and then we can find out the reflection and transmission coefficients. So this is what boundary conditions are. So this is our potential step, and the boundary is at x is equal to 0. Now our first boundary condition is that the wave function in region 1 should be same as wave function in region 2 at the boundary. So our first boundary condition is boundary condition 1 is psi 1 should be same as psi 2 at x is equal to 0, where psi 1, let me write it, is a into e to the power I kx plus b into e to the power minus I kx, where k is square root of 2m e by h cross square, and psi 2 is c into, oh sorry, it's d, I guess, d into e to the power minus k prime x, where k prime is square root of 2m, it's a positive term, v0 minus e by h cross square. So this is psi 1 and psi 2, and therefore at x is equal to 0, what I get is a into e to the power e to the power 0 is 1, at x is equal to 0, simply a, plus second term is also simply b, is equal to, for psi 2 it is d, because all the exponentials they become 1 when x tends to 0. So this is our first boundary condition, a plus b is equal to d. Now let's consider the second boundary condition. So it's boundary condition 2 now. In second boundary condition, the first order derivative of psi with respect to x should be same in both the regions, and therefore d psi 1 by dx should be same as d psi 2 by dx, where psi 1 I have written, we have obtained it as a into e to the power I kx plus b into e to the power minus I kx, and therefore d psi 1 by dx is I k a e to the power I kx minus I k b e to the power minus I kx, and psi 2 is all real, d into e to the power minus k prime x, and therefore d psi 2 by dx is minus k prime d into e to the power minus k prime x. And now if we use the boundary condition that at x is equal to 0, d psi 2, oh sorry, d psi 1 by dx should be same as d psi 2 by dx. What we get is, I can take ik common in this, on this left hand side, and therefore what I have is ik, and this is now a minus b is equal to d. So this is my second boundary condition. Let me once again write both the boundary conditions. So the first boundary condition is a plus b is equal to 0, and the second boundary condition is ik a minus b is equal to k prime d. Okay, now let's first calculate the reflection coefficient R. Remember, reflection coefficient is probability that a particle when incident on the step is reflected. So it is probability of reflection. Okay, this is reflection. In other words, if I consider that I have a stream of n number of particles, then probability of reflection is basically the fraction of the particles which are reflected from the boundary. And this R therefore can be calculated by considering the probability current density, or rather it is the ratio of probability current density of reflected, which we have written like this, to incident wave. So this will give us the probability of reflection when it is incident on the boundary. And if you can recall, this J reflection reflected is H cross K by M into mod B square divided by J incidence is H cross K by M into mod A square. I hope it's correct. Let me go back and confirm that I have written it correctly. J reflected H cross K by M into B square. That's right. So let's now calculate the reflection coefficient, and you can see that this term in the bracket will cancel, and in the end I have mod B square by mod A square. So we first have to find B in terms of A to find R, and this can be done with the help of the two equations that we have obtained by using the boundary condition. Our first equation is A plus B is equal to D, and the second equation is IK, A minus B is equal to minus K prime D. Is it correct? Okay, IK A minus B is, it's minus or plus? It has to be minus here. Yeah, it seems all right. So this is the second equation that we have. Now I have to solve these two equations and to obtain B in terms of A, and for that I'll do is I'll use the first equation, this equation, and plug in D as A plus B, and therefore what we get is this. So this is first equation, this is second equation. So plugging D from equation 1 into equation 2, what I get is IK A minus B is equal to minus K prime A plus B. So this equation now has only A and B, and therefore I should be able to write A in terms of B. So let's do it. Let's collect all the terms with A on the left hand side. So what I have is I K and plus K prime, and on the right hand side I'll have all the terms, both the terms with B, which are with a negative sign now, and they are minus B into, or okay, let's first write the first term, so which is positive term, IK minus K prime. Is it correct? So therefore what I have here is B by A is equal to, yeah, I want B by A, so it is therefore equal to IK plus K prime divided by IK minus K prime, and this is the ratio. What I want is mod B square. So B by A I have, and I'll now find out mod B square by mod A square. Uh, to finding the mod B square by mod A square is basically multiplying the right hand side by its complex conjugate, and therefore that is now equal to IK plus K prime into minus I k plus k prime, because that is its complex conjugate. I have to reverse the sign of the imaginary part, and same here in the denominator, I k minus k prime into, now it is minus I k minus k prime, and now I have mod b square by mod a square, which happens to be the reflection coefficient, which is equal to, now it is simple, I don't have to go on expanding the bracket. It is, what I have is something like this. I have a complex number x, oh sorry, z, which is x plus iy, and I'm multiplying that complex number by its complex conjugate x minus iy, and this z square, after multiplying the two by multiplying the complex conjugate, multiplying the complex number by its complex conjugate, will simply be equal to x square plus y square. And if you don't know this already, you can convince yourself by expanding the brackets, and therefore in this case what I should get is k plus k prime whole square, or rather it's k prime square plus k square divided by k prime square plus k square. So therefore r turns out to be equal to 1. So reflection coefficient is 1, which means that probability of reflection is equal to 1. Okay, now let's find the transmission coefficient T, which is going to be by the same lines, J transmitted divided by J incident, but we already have figured out that J transmitted, probability current density of the transmitted particle, is equal to 0, and therefore T is equal to 0, and this should be obvious. Why? Because R is the reflection coefficient, it is the probability that the particle is reflected, whereas T is transmission coefficient, or the probability that the particle is transmitted. And since these are the only two possibilities that can happen, the particle when incident on the boundary will either transmit or reflect. Therefore, probability should add up to 1. So if R is already 1, T should be equal to 0. We don't really have to calculate this, but um, we can verify here that actually this equation is what we can anticipate already. So this is the result that we get for this case, E less than V0. Now let's try to understand the significance of this result. So let me for that draw the potential step once again. It's like this, where this is the boundary which is at x is equal to 0. This height is V0, and this here the potential is equal to 0. So we have the incident particle, and it is now represented by the traveling wave, and it is like this. Now this a is the amplitude of this wave, which is the coefficient of that e to the power I kx. Now the reflected wave is b into e to the power a kx. So the refracted wave also has the same wavelength as the incident wave. However, in this region 2, which is classically forbidden region, because the particle doesn't have sufficient kinetic energy to overcome this step, the particle classically will be always reflected, which is the same result that we have obtained. But now in this case, in region 2, the wave function is not entirely 0. We calculated psi 2, and that is equal to d into e to the power minus k prime x, and since d is not 0, and why can't it be 0? It cannot be 0 because we know that a plus b is equal to d, so therefore d cannot be 0 there, and therefore this wave function when you plot is something like this. It is exponentially decreasing because of this e to the power minus k prime x. But remember that mod psi 2 square is the probability density of finding the particle, and you can see now that even in region 2, in the so called classically forbidden region, there is the finite part probability that the particle is found there. So you actually make measurements for a large number of time to see whether the particle is present in region 2 or not, and it will turn out once in a while that the particle will be really found in region 2, and this is not classically intuitive. It goes against the predictions of classical mechanics and our intuitions, because we live in the classical world. So this is not what we expect classically, and this is something surprising in that sense. So what we have is, we don't have the traveling solution in the classically forbidden region, but yet there is finite probability, a non-zero probability, that the particle is found in that region. So this is how the classical mechanics and quantum mechanics differ in their predictions for the treatment for this case. Now let's move on to the second case when E is greater than V0. So case 2 now. Let me again draw the potential step. So this is our potential. This is the boundary at x is equal to 0. And now what we are considering is E greater than V0. So our incident particle is incident from the left to right. It is traveling from minus infinity towards positive side of x. It encounters the boundary here, and its energy now, kinetic energy, is greater than V0. This height, remember, is V0, and this, if we try to anticipate what classical, or if we try to guess what classical results are here in this case, since the particle has positive kinetic energy even in region 2, the particle will continue to move in the same direction. There is no chance classically that the particle is reflected from the boundary. So this is what classical mechanics predict, and therefore classically saying, so classical prediction says that T should be equal to 1. T is the transmission coefficient, probability that particle is transmitted. R is equal to 0. There is no probability that the particle is reflected. Let's now see what quantum mechanics has to say for this problem. So we of course will start by writing the Schrodinger's equation. Let me write the Schrodinger's equation, Schrodinger's time independent equation first. In general, it is h cross square by 2m for one dimensional case, psi d2 psi by dx2 plus v, which is in general function of x, into psi is equal to E into psi. Remember, psi here is function of x, so I haven't written it explicitly. So this is the Schrodinger's equation. So let's now write it for these two regions. This is region 1, and now this is region 2. Sorry, this is region 2. And remember, now for the previous case, region 2 was classically forbidden, whereas in this case it is not. So let's first write region 1, Schrodinger's equation in region 1. V there in region 1 is equal to 0, and therefore our equation is, let me skip the step, it is going to be same as uh, solution for region 1 for the previous case. It is a into e to the power I kx plus b into e to the power minus I kx, where k is this positive constant 2me by h cross square, right? So this is what is the solution in region 1. Remember that this represents the incident particle, the incoming particle. So it represents the incident particle, or it gives us uh, the probability density of incident particle. This term represents the probability density of reflected particle. Because of this minus k, it corresponds to negative momentum, and therefore that term is basically uh, a wave equation, or a matter wave which is moving in negative x direction in region 1, and therefore is negative. In second region, let's write the equation, Schrodinger's equation in region 2. Now it is minus h cross square by 2m. This is d2 so okay, I'll d2 psi 2 by dx2 is equal to, the second term now is no longer 0, it is rather positive, b0 psi 2 into e psi 2, where e is greater than b0, right? So this is the equation. So let's now move on to the next slide and do some mathematical jugglery to obtain the Schrodinger's equation in the desired form. So this is now therefore d2 psi 2 by dx2 is equal to, what is it? So it is e minus v0 now. So this is minus 2m e minus v0 divided by h cross square into psi 2, where e is greater than v0, and therefore this equation can be written as d psi 2 by dx2 is equal to minus k prime square psi 2, where k prime is square root of 2m e minus v0 divided by h cross square. And remember, this is also a positive, so k prime is greater than 0, it's a positive constant. And if you don't get confused here in the notations, I'm using the same as for k prime and psi 2, but they have a different meaning. In the previous case, k prime was this quantity which was, I mean, in the previous case, this negative sign wasn't there, whereas in this case we have that negative sign, and therefore due to that negative sign, the solution to this equation now is a traveling wave solution. It's a complex solution, and psi 2 turns out to be equal to c into e to the power I k prime x plus d into e to the power minus I k prime x, where k prime is this positive constant. And now both these terms are traveling wave solutions. This represents particle in region 2 which is traveling towards positive x-axis, whereas the second term represents the particle which is traveling in the negative x direction in region 2. So can you now tell me which of these two terms cancel, because uh, one of them cancels, so can you tell which is the term which should not be there? Physically it is insignificant. Okay, hope you have the answer. I'll answer that now. So this is our potential step, and the first term is a particle which is traveling in this direction, so it gives you, this term is e to the power, or rather let's draw a wavy pattern because we are talking about the matter waves. This is the matter wave which is traveling in this direction, c into e to the power I k prime x, whereas if you consider the second term, this is term which is again a wave, but this wave now is traveling in negative x direction, and it is mathematically written as e to the power minus I k prime x. Now in second region, here after x is equal to 0, there is nothing physically which can cause the particle to reflect, and therefore we can expect that this second term should not be there. This wave is not present at all in the solution, and therefore I can ignore the second term, which is a wave which is traveling in negative x-axis in region 2, because that wave is not there. There is nothing in that region which can reflect the wave, and therefore psi 2 is simply c into e to the power I k prime x, where k prime is, remember, okay, I have written it, so I'll simply draw a box around that k prime. So this is k prime, and this is our solution in region 2. So again we will follow the same steps that we have taken in the previous case. We will now first consider the boundary condition. We will first consider the probability current density for each of them, and then by using the boundary conditions, we will try to figure out what are the transmission and reflection coefficients. So now first, oh, we already have considered the solution, so I can skip this step. Okay, so let's now consider the probability current density. So let's first consider J incident. J incident is, okay, first let me write psi incident, which is A into e to the power I kx, where k is the constant. You can go back and have a look of what that constant is. J reflected is b into e to the power minus I kx, and J transmitted is c into e to the power I k prime x now. So these are the wave functions, and we have to find out J for each of these wave functions. This is incident, reflected, and transmitted. Remember, J is, in general, the equation is I h cross by 2m psi star, oh, sorry, this is not psi star, psi into d psi by dx minus psi star into d psi by dx. This is complex conjugate. Okay, so you can again try to find out what J incidence is, or you can simply go back and see what J incident, the probability current density for incoming particle is. It is h cross k, oh sorry, yeah, h cross k by m into mod a square. J reflected, or probability current density for reflected particle, is h cross k by m into mod b square, and the transmitted particle J transmitted now is h cross k by m into mod c square. So this is something which was not same in the previous case, because there we got J transmitted to be equal to 0 because the wave function was real. These two terms were same in that case for J psi transmitted. When we calculated J transmitted, these terms cancelled each other, and therefore we got it to be 0. But now that is not the case. We have a traveling wave solution even in the region 2, which is of course not classically forbidden. So these are the probability current densities here. And now using these probability current densities, I have to find out the reflection and transmission coefficient. So let's do it. For that, we of course have to consider the boundary conditions first. So let's first consider the boundary conditions. What is the first boundary condition? The first boundary condition is, so condition 1 is wave function in region 1 should be same as wave function in region 2 at x is equal to 0. At the boundary of the potential well, both these wave functions should be same, they should match. So we are now matching the wave function at the boundary. And psi 1, okay, I'm sorry, the slide has okay, so psi 1 is a into e to the power minus I kx plus b into e to the power, oh, this is positive and this is now negative I kx, whereas psi 2 is c into e to the power I k prime x, right? So if I use the first boundary condition, what I get is a plus b is equal to c. So this is the equation that I obtained by using the first boundary condition. Now boundary condition 2 is this: the first derivative of wave function with respect to x should be same for psi 1 and psi 2 at x is equal to 0, of course. So we are matching the first derivative of the wave function at the boundary for the two regions. And if I do it, you can I'll straight away write the equation, and what I'll get is this. I'll get ik a minus b is equal to, when I differentiate this, I get I k prime c, and that's all. Is it correct? Yeah, it seems all right. So this I cancels and I have this equation. K into A minus B is K prime into C. So let me, okay, so let me write it here in this box. So what I have is the first boundary condition is A plus B is equal to C, and the second boundary condition is A minus B is equal to K prime by K into C. Okay, so let's now find out the transmission coefficient and reflection coefficient. Let's find transmission coefficient first. We'll denote it by P, which is probability that the particle is transmitted from the barrier, which classically should be equal to 1. Let's see what we get at quantum mechanically. So this T transmission should be the ratio of J transmitted divided by J incident, and this is now H cross the H cross K prime divided by M into mod C square divided by H cross K by M into mod A square. So this H cross and M will cancel, and what we have is K prime by K into mod C square by mod A square. So we now first have to figure out this ratio mod C square by mod A square to calculate T. And for that we have our boundary conditions handy. A plus B is C and A minus B is what was it? K prime by K into C. So to obtain this ratio, I have to now get rid of this B, and that is easy. I can simply add the two equations. This is my first equation and this is the second equation which I have obtained by using the boundary conditions. If I add them, I get 2A is equal to C into 1 plus K prime by K, or uh, 2A is equal to C into K plus K prime divided by K. So therefore I can now have C by A ratio is, let me write it here so I have sufficient space. So C by A is, what is it, 2K divided by K plus K prime. So this is what I have, 2AK plus divided by. Okay, so what is transmission coefficient then? T is equal to, I have that K prime by K here, and then I have this C by A, which is 2K divided by K plus K prime, and now this K cancels and T turns out to be equal to 2K prime K plus K prime. Hey, am I making a mistake? Yeah, it's squared. Oh, I'm sorry, this cannot cancel. I'm sorry, this cannot cancel. This is squared here. Let's not forget that. So what I have is K prime by K into 4K square divided by K plus K prime whole square. So T is therefore, now one of the K cancel. It is 4K into K prime divided by K plus K prime. Yeah. So this is the transmission coefficient or probability that the particle is transmitted. Okay, so let's now calculate the reflection coefficient. Now there are two ways to calculate the reflection coefficient. I can consider this ratio of J reflected to J transmitted, or I can simply subtract uh, T from 1 and calculate R. What I'll do is I'll calculate it explicitly. So I'll calculate this ratio of J reflected to J transmitted, probability ratio of probability current density. Remember, R is the probability that the particle is reflected when it is incident on the boundary for this case when E is greater than V0, and it is now H cross K by M. J reflected is this into mod B square divided by transmitted. This is incident. I'm sorry. And this is H cross K by M, and this is mod A square. is equal to 1. The division is 1, and I have mod b square by mod a square. So I have to find this ratio. Again, I can use the equations which are obtained by boundary condition. These are the equations. E minus b now is a prime by k into c. So now I have to solve these two equations and obtain this ratio of b by a somehow. And for that, what I'll do is I'll use the first equation and we'll replace the c in the second equation as a plus b, so that I have only a and b in the equation. So I have a minus b is equal to k prime k, and c is a plus b. This is what I'm doing. So what I have is, therefore I'll collect all the terms on left hand side with a now. So it's 1 plus, oh sorry, minus k prime by k, and this is equal to b into all the terms which have b. Now I have addition here, 1 plus k prime by k, and therefore what I have is, let me write here. So I have a into k minus k prime divided by k. This is equal to b into k plus k prime divided by k. So this cancels, and I have b by a as, what is it? It is k minus k prime divided by k plus k prime. So this is what we have, and therefore mod b square. Let me write it on the next page. So mod b square by mod a square. Okay, so let's write r itself. R is, this is now k minus k prime whole square divided by k plus k prime whole square. So this is the reflection. This gives the probability that the particle is reflected, and transmission coefficient is here. Now let's see the significance of the result. First, what I will do is we will verify that r plus t should is equal to 1, because that is, r and t are probabilities of reflection and transmission respectively, and since these are the only two possibilities that can occur, the probabilities should add up to 1. Let's first see that. Let's first calculate r, or rather t plus r. Now t is what? It is 4k prime divided by k plus k prime squared, and plus, right, and this is k prime minus k, isn't it? K minus k whole square divided by k plus k prime whole square. So let's see what we have. This is equal to 4k k prime. They happen to have the same denominator, so I can simply add them. This is k square plus k prime square minus 2k into k prime divided by k plus k prime whole square. So this is, you can verify the denominator is also k plus k prime whole square, because this 4k k prime and minus 2k k prime will add to 2k k prime, and that is simply k plus k prime square, and this also is k plus k prime whole square. So this is equal to 1. So this is the first, here we can verify, uh, or at least have a first check whether we have derived r and t correctly or not. So this is our first significance to the result. Now the second significance, second thing that we have obtained. So the second significance, or another significance that we can have from here is this. For that, let me write the equation for r. R is equal to, I'm sorry, so this is a spoiler. It is r. R is k minus k prime whole square divided by k plus k prime whole square, where k is 2m e by h cross square under root, and k prime is 2m e minus v0 by h cross square. So this is k, k prime and b. So first notice that since k and k prime are not same when there is the potential shift, no matter how small it is, this difference when it's not equal to 0, r is non-zero. So that is the first thing that we notice, that unlike classical case where the particle will always transmit and will never reflect, quantum mechanically, or if we do this experiment with very small particles, we will observe that some of them reflect even when they have sufficient energy to transmit through the barrier. Okay, let's now consider a very uh, interesting problem, slightly different than the previous one. We again have the negative step, but now in this case is what we have considered, the particle is moving from zero potential region to a region with non-zero potential. We can now invert this in the sense that initially the particle is traveling with some potential, and then the potential is zero in this region, or you can say that uh, it's a negative step potential. So V is zero in this region. At the boundary, the potential drops, it becomes some negative of V0, where V0 is a positive constant, and the particle now is again traveling from, okay, sorry, is again traveling from negative, what's that now? So the particle is traveling from negative to positive x, and now if you write the Schrodinger's equation, the same steps that we have do some mathematical jugglery, and you can convince yourself that we get very similar results for r and k, r and t, where r is the transmission coefficient, which turns out to be equal to k prime minus k whole square, or k minus k prime whole square divided by k plus k prime whole square, and t is 4k square divided by k plus k prime. The same equations basically, but the values of k and k prime are now different. K is 2me by h cross square, whereas k prime is 2m plus V0 by h cross square. In the previous case, case 2 of positive potential step, we had this as E minus V0. This bracket was E minus V0, which is now E plus V0. And what we get therefore is T turns out to be equal to, let's focus on T, what we have. So basically what we are seeing is the potential is 0 as the particle travels, and suddenly at x is equal to 0 the potential drops to a negative value, and therefore classically uh, the force is exerted on the particle in such a way that the particle is accelerated to some higher velocity. So the velocity of the particle will increase, its kinetic energy will increase there, it will get an impulse, and therefore its kinetic energy will increase in that case. Let's now see what happens quantum mechanically. Let's focus on on this transmission coefficient T and see what we get. Let's do some maths here. So T is 4k square. I'll divide the whole equation by k square in the numerator and in the denominator, and therefore what we have is k plus k prime by k whole square, where k is 2me by h cross squared, and k prime is also positive, 2me plus v0 by h cross. Now we can consider two cases. One is, first thing that you should notice is probability of reflection is still non-zero. Let me write the equations somewhere else. Okay, so again notice here that the probability of reflection is non-zero. Classically, uh, it's always zero, but in this case it is definitely non-zero. The second case that you should notice is that when the step has the depth of the step is compared to the total energy, which what I mean by that is we have this energy where this is energy of the particle when the potential is 0, and now the depth is comparable to the energy. This is V0. So that is what I mean by E comparable with V0. They have similar values. And when this happens, let's see what happens to T. T is 4 divided by 1. So this has to be 1 in this equation. 1 plus K prime by K whole square. So for when K and K, when E and V0 are same, K and K prime are almost same, and therefore this is equal to 1. So when the energy and the depth of the well is comparable, which is similar to saying that the well is not there. So which is similar to saying that the depth of well is not very large as compared to the energy, then the probability of transmission is more. But if we consider the second case, when the depth of the uh, well is small as compared to total energy, then we have the reverse situation, and then T is equal to 0, whereas R is equal to 1. So you can use the similar formula and do the maths for yourself. We will stop here. It's already a very long lecture. So this is what we discussed. We described the one-dimensional potential well. Consider these two cases. And the first case where E is less than V0 was quite similar to what classical mechanics predicts, except that in the classically forbidden region there is finite probability that the particle is present, whereas for this second case the particle always transmits, it never reflects. But we found out that in quantum mechanically there is a finite probability that the particle is reflected. Of course, as the difference between the potential step and energy goes on increasing, this probability of reflection goes to 0. You can try that. I'm leaving that as homework. And for negative step, though we didn't solve it with all the mathematical rigor, we simply took the solutions from previously solved cases, and we could see that it is also drastically different, because the reflection should be 0 classically, but quantum mechanically it turns out to be non-zero. And then two other things that two cases that we considered, for two limits that we considered there. We will stop here. Thank you for watching this video, and I want you to complete the homework, which is to solve the negative potential step and obtain the relations for transmission and reflection coefficient.